Hello everyone. Today we are going to analyze this beam using flexibility matrix method. Before analyzing, let us see the beam one time. In this beam, there are two spans, span AB and span BC. In the span AB, there is a point load 50 kN acting at 2 meter from the point A. In the span BC, there is uniformly distributed load 24 kN per meter acting for the full span. In the point A and in the point C, we are having fixed supports. In the point B, there is a hinged support. Span AB is 5 meter long. Span BC is also 5 meter long. In this beam, the number of unknown reactions and moments are 5. They are MA, MC, RA, RB and RC. The available equilibrium equations are 2. Summation of moments is equal to 0 and summation of vertical forces is equal to 0. So the degree of static indeterminacy is equal to 5 minus 2. We will get 3. Let us remove MA, MB and MC so that this statically indeterminate beam changes into two statically determinate simply supported beams. This is called the released structure. We have made the released structure. Now let us make the coordinate diagram. In this analysis, we are having three coordinates. In the point A, in the point B, and in the point C, we are having the coordinates. Because in these points only we have removed the moments. Let us keep the coordinate in the point A in the clockwise direction and let us keep the coordinate in the point C in the anti-clockwise direction. The point B is a joint, so the second coordinate will be acting in both of the directions. Now let's see the formula to calculate the moments. P matrix is equal to delta matrix inverse into delta matrix minus delta L matrix, where P matrix is the final moments or forces, delta matrix is the flexibility matrix, delta matrix is the final displacements, delta L matrix is the displacement in the coordinate direction. Inside the delta L matrix and delta matrix, we will have three values. Because we are having three coordinates in this analysis. In this formula, first let us calculate delta L matrix. To find delta L matrix, we have to make the conjugate beams. Let us calculate the ordinate for conjugate beams. If in the simply supported beam, the point load is not acting on the center, the formula for the maximum bending moment is WAB upon L. Here W is 50, A is 2, B is 3, L is 5. When we apply the values inside the formula, we are getting 60. If in the simply supported beam, UDL is acting for the full span, the formula for the maximum bending moment is WL square upon 8. Here W is 24, L is 5. When we apply the values inside the formula, we are getting 75. We know that in the conjugate beam, we have to divide the bending moment by EI. In the delta L matrix, we have to calculate three values. Delta 1L should be calculated from the first coordinate. Delta 2L should be calculated from the second coordinate. Delta 3L should be calculated from the third coordinate. Now let us calculate delta 1L. For that we have to find the slope at the point A. In the conjugate beam, the slope is the shear force. In the point A dash, the shear force is the reaction RA dash. We can apply a formula to calculate RA dash easily. If UVL is acting in a simply supported beam in the shape of unsymmetrical triangle, the formula to find RA is W upon 6 into L plus B. Let us apply the formula and find out RA. Here W is 60 upon EI, L is 5, B is 3. When we apply inside the formula, we are getting 80 upon EI. So delta 1L is equal to 80 upon EI. Now let us calculate delta 2L. For that we have to calculate RB dash. We have to calculate RB dash 2 times. First from the first beam, then from the second beam. First let us calculate RB dash in the first beam. The formula to calculate RB dash is W upon 6 into L plus A. Here W is 60 upon EI, L is 5, A is 2. When we apply the values inside the formula, we are getting 70 upon EI. Now let's calculate RB dash in the second beam. If in the simply supported beam, UVL is acting in the shape of parabola, the formula for RA and RB is WL upon 3. In the formula, let's apply the values. W is 75 upon 3 and L is 5. After applying the values inside the formula, we are getting 125 upon EI. After adding, we are getting delta 2L, which is equal to 195 upon EI. Now let us calculate delta 3L. For that, we have to find RC dash. We have already seen the formula for the reaction WL upon 3. Here W is 75 upon EI, L is 5. When we apply the values inside the formula, we are getting 125 upon EI. Let us enter the values inside the delta L matrix. 1 upon EI is constant. Let us take it outside. In this formula, we have calculated delta L matrix. Now let us calculate delta matrix. If in the beam there is overhanging, we have to calculate the delta matrix. Otherwise, we can simply enter 0. In the given beam also, there is no overhanging. So we can simply enter 0 inside the matrix. The size of the matrix will be according to the coordinates. In this analysis, we are having 3 coordinates. So we are having 3 values inside the matrix. All of the values are 0 because we are not having any overhanging in the given beam. In this formula, we have calculated delta L matrix and a delta matrix. Only one is remaining to be calculated, that is the flexibility matrix. Now let's see how to calculate the flexibility matrix. Now let's see the size of the flexibility matrix. For 3 coordinates it will be 3 by 3. For 2 coordinates it will be 2 by 2. For 1 coordinate it will be 1 by 1. In this analysis we are having 3 coordinates. For 3 coordinates the size will be 3 by 3. Inside the matrix we will have 3 rows and 3 columns. Now let us calculate the first row in the flexibility matrix. To calculate the first row, we have to apply unit movement in the first coordinate. When we apply unit movement in the first coordinate, here the movement will be 1 and here it will be 0. Using that we can draw the diagram. We know that in the conjugate beam, we have to divide the moment by EI. So we have to divide this one by EI. Now let us calculate delta 11. For that we have to find RA dash. Here we can apply the formula and find RA dash very easily. In this kind of load in the simply supported beam, the formula for RA is WL upon 3. Here W is 1 upon EI, L is 5. When we apply inside the formula, we are getting 5 upon 3 EI. Now let us calculate delta 12. For that we have to calculate RB dash. The formula is WL upon 6. Here W is 1 upon EI and L is 5. When we apply inside the formula, we are getting 5 upon 6 EI. In this beam, there is no load, so RC dash will be 0. In this case, delta 13 will be 0. Now let's find the second row in the stiffness matrix. For that, we have to apply unit movement in the second coordinate. When we apply unit movement in the second coordinate, here the movement will be 1 and here the movement will be 1. Here it will be 0 and here it will be 0. Using that, we can draw this diagram. Now let us calculate delta 21. For that, we have to find RA dash. Let us see the formula. In this kind of loading, RA is equal to WL upon 6. Here W is 1 upon EI, L is 5. When we apply inside the formula, we are getting 5 upon 6 EI. Now let us calculate delta 22. For that, we have to find RB dash. We have to find RB dash in both of the beams. First, let us calculate in the first beam. The formula is WL upon 3. Here W is 1 upon EI and L is 5. When we apply inside the formula, we are getting 5 upon 3 EI. Now let us calculate RB dash in the second beam. The formula is WL upon 3. Here W is 1 upon EI and L is 5. When we apply inside the formula, we are getting 5 upon 3 EI. Let us add these two values and find out delta 22. Now let us calculate delta 23. For that, we have to find RC dash. The formula is WL upon 6. Here W is 1 upon EI and L is 5. When we apply inside the formula, we are getting 5 upon 6 EI. Now let's calculate the third row in the stiffness matrix. For that, we have to apply the unit displacement in the third coordinate. When we apply the unit displacement in the third coordinate, here the movement will be 1 and here it will be 0. Using that, we can make this diagram. Now let us calculate delta 31. For that, we have to find RA dash. RA dash will be 0 because in this beam there is no load. So delta 31 is equal to 0. Now let's calculate delta 32. For that, we have to find RB dash. The formula is WL upon 6. Here W is 1 upon EI, L is 5. When we apply inside the formula, we are getting 5 upon 6 EI. Now let us calculate delta 33. For that, we have to find RC dash. The formula is WL upon 3. Here W is 1 upon EI and L is 5. When we apply inside the formula, we are getting 5 upon 3 EI. In the flexibility matrix, we have calculated all of the rows. 1 upon EI is constant. Let us take it outside. In this formula, we have calculated everything. We can apply the values. 1 upon EI inverse is equal to EI. Then we can add these two matrices. After adding, we are getting this. Then we can eliminate this EI and this EI. For this matrix, we have to find the inverse. We can apply all of the values inside the calculator and find out the inverse. If you do not know how to find the inverse of 3 by 3 matrix, see the description below. There is a link. You can click the link and watch the video for getting ideas how to find the inverse of 3 by 3 matrix. I have used the calculator and found the inverse. When we multiply these two matrices, we will get the final moments. The moments will be according to the coordinates. The first coordinate is in the point A. So first we will get MA. The second coordinate was in the point B. So here we will get MB. The final coordinate is in the point C. So here we will get MC. So in this analysis, we have calculated all of the moments. Now let us calculate the reactions. To calculate the reactions, we have to split the beam according to the spans. There are two spans AB and BC, so we have to split the beam into two parts. In the span AB, MA will be acting in the anticlockwise direction and MB will be acting in the clockwise direction. In the span BC, MB will be acting in the anticlockwise direction and MC will be acting in the clockwise direction. Now let us take the span AB and calculate the reactions. In the span AB, first I am going to find RA. For that, I am going to take moment about B. In this case, I am moving towards right hand side. Clockwise will be positive and anticlockwise will be negative. The vertical reaction RA is acting towards the point B in the clockwise direction, so it will be positive and the distance is 5. So 5 RA. The point load 50 kN is acting towards the point B in the anticlockwise direction, so it will be negative and the distance is 3 meter. So minus 50 into 3. Then there are two moments. The moment 29.5 is acting in the anticlockwise direction, so it will be negative. The moment 37 is acting in the clockwise direction, so it will be positive. After the calculations, we are getting RA is equal to 28.5 kN. To calculate RB1, let us apply the rule summation of vertical forces is equal to 0. In this span, there are three vertical forces RA, RB1 and the point load 50 kN. The reactions RA and RB1 are acting upwards, so both of them will be positive. 50 kN is acting downwards, so it will be negative. We have already calculated RA 28.5, so instead of RA, let us apply 28.5. In this way, we can calculate RB1, which is equal to 21.5 kN. Now let us take the span BC and calculate the reactions. In this span, first I am going to calculate RB2. For that, I am going to take moment about C. The vertical reaction RB2 is acting towards the point C in the clockwise direction, so it will be positive and the distance is 5. So 5 RB2. The UDL 24 kN per meter is acting towards the point C in the anticlockwise direction, so it will be negative. When the UDL comes, we have to multiply with the distance and a distance upon 2. Here the distance is 5 meter, so 5 into 5 upon 2. Then there are two moments. The moment 37 is acting in the anticlockwise direction, so it will be negative, and the moment 56.5 is acting in the clockwise direction, so it will be positive. After the calculations, we are getting RB2 is equal to 56.1 kN. Now let us apply the rule summation of vertical forces is equal to 0. In this span, there are three forces RB2, RC and the UDL 24 kN per meter. RB2 and RC are acting in the upward direction, so both of them will be positive. The UDL is acting downwards, so it will be negative. For the UDL, we have to multiply with the distance to get the total load. We have already calculated RB2. Let us apply the value. In this way, we are getting RC is equal to 63.9 kN. We have calculated the reaction in the point B 2 times. Let us add both of the values RB1 and RB2. After adding, we are getting RB, which is equal to 77.6 kN. Now we are going to draw the shear force diagram. Before drawing, Let us find the shear force values. I am going to calculate the shear force values from the point A and towards the point C. In this case, I am moving towards right hand side. Upwards will be positive and downwards will be negative. You can see the calculations here. Using the values, we can draw the shear force diagram. Now, we are going to draw the bending moment diagram. For the bending moment diagram, first we have to make the free moment diagram, then end moment diagram. Finally, we have to combine both of them to get the bending moment diagram. For the free moment diagram, we have to assume each span as a separate simply supported beam and calculate the moments. In this analysis, we have already calculated the ordinates initially. Using them, we can make this diagram. Using the end moments, we can make the end moment diagram. Now, let us combine the free moment diagram and end moment diagram to make the bending moment diagram. You can see that I have combined both of the diagrams. Wherever they are acting alone without mingling with one another, we have to mark the values with the sign. Here the end moment diagram is coming alone. Here the free moment diagram, then end moment diagram, then free moment diagram, finally the end moment diagram. Wherever they are together, we are not marking anything. We just keep the space empty. Now we are going to end this session. Thank you for watching this video.